talk to you guys about the Wyrm. The Wyrm is something that I'm really proud of our team for creating because it's something that started as literal hand sketches that we turned into a fully functional prototype. This is something we submitted to RoboSoft 2022, which was a soft robotics conference. Soft robotics is the field of robotics dealing with stuff that's squishy. Every year people submit really cool, soft, compliant robots to RoboSoft 2022. And these robots pick stuff up, they're assistive medical devices, they can be used for transportation, they have a number of different applications. Students like us get to use their robots in a competition format. So we decided to enter the terrestrial race, in which we were going to have to go over sand, go over a ramp, and then dodge a bunch of obstacles. In the beginning, we didn't know what the project guidelines were going to be. All we really knew was that our robot had to be squishy and it had to move. Knowing this, we brainstormed a bunch of different robots. We used a decision matrix to narrow it down, and we came up with an inchworm robot. So we created a bunch of cool SolidWorks models for this inchworm robot. We had this really cool idea for like silicon chambers that would contract and expand, and then our materials didn't come for like 3 weeks, so we were kind of just sitting there thinking of what to do. So we started playing with balloons. What we did was we constructed a rudimentary McKibben air muscle. We worked with that, and we found that we had a pretty good way for compressing the robot together. We just needed a way to expand it back out. So we started integrating springs into it. And that didn't work super well at first because it was like flexing. What we decided to do was encase the entire air muscle inside of a spring. And Josh came up with this 3D printed spring that the muscle could fit perfectly inside of. The balloon kept popping, so Valerie and I had to mold a bunch of silicon bladders to insert inside of the McKibben air muscle. But this ended up working really well. We were able to get the robot to move, and then that was our robot for like about a month. The steering system was the same silicon bladders that were inside McKibben air muscle, but they were glued together so that you could inflate one and then the other, and then it would make like a turning motion.
Moves.
So funny.
Not very controlled, but
That's the bad one, so we're not going to use. We ended up having a lot of trouble controlling that. So it didn't make it onto the final version of the robot. We also tried to create feet that would grip the ground when necessary, so that when the robot was inching, it could grip the ground in between steps. We tried to do this with a pneumatic system at first, but that didn't really work too well, so we switched to servos. And then once we switched to servos, we found that we could kind of move the robot just by flapping the servos up and down. And we found that since the old steering mechanism wasn't working so well, we could kind of just ditch the steering mechanism altogether, and we could just use the servos to rotate the robot clockwise or counterclockwise. The final version of the robot ended up having flapping servos that would control its clockwise or counterclockwise motion, and a McKibben air muscle that would inch the robot forward. Combining these methods, along with a sonar sensor and a bunch of code, we were able to create an autonomous robot that could navigate an obstacle course and get over a bunch of different terrain.